Download this code from codegive.com, link in the description below. Compose Runtime and Performance, a deep dive for Android developers. Compose, Android's modern UI toolkit, offers a declarative and efficient way to build user interfaces. However, understanding its runtime behavior and performance characteristics is crucial for crafting performant and scalable apps. This tutorial delves deep into Compose's inner workings, exploring how it manages state, recomposition, and rendering, with practical code examples and performance optimization strategies. 1. Understanding the core concepts. Before diving into performance, let's establish a solid understanding of the fundamental concepts behind Compose. Declarative UI. Unlike traditional imperative UI frameworks, like views, Compose focuses on what the UI should look like, rather than how to change it. You describe the desired UI state, and Compose handles updating the view hierarchy accordingly. Composable functions. These are the building blocks of Compose UI. A composable function emits UI elements, and it can also handle state and logic. They're annotated with @composable. State management. In Compose, state is what drives your UI. When state changes, Compose recomposes the parts of the UI that depend on that state. In this example, mutable state of 0 creates a state variable that holds an integer, initialized to 0. Remember is used to ensure that the state persists across recompositions. When the button is clicked, count++ updates the state, triggering recomposition. Recomposition. This is the core mechanism by which Compose updates the UI. When a composable's input parameters, including state, change, Compose re-executes that composable function and updates the corresponding UI elements. Composition. The overall structure of the UI created by executing composable functions. Think of it as the output of your Compose code. Layout and draw. After recomposition, Compose needs to lay out the UI, determine the position and size of elements, and then draw them on the screen. 2. The Compose runtime in detail. The Compose runtime is responsible for managing the recomposition process, optimizing updates, and ensuring efficient UI rendering. The recomposition scope. Compose uses a concept called a recomposition scope to track which parts of the UI need to be recomposed. This scope is essentially a data structure that records dependencies between composable functions and the state they read. Dependency tracking. When a composable function reads a state variable, the Compose runtime automatically establishes a dependency between that composable and that state. This dependency information is stored in the recomposition scope. Invalidation. When a state variable is updated, example by calling count++ in the counter example, the Compose runtime invalidates all composables that depend on that state. This means that these composables are marked as needing to be recomposed. Scheduling recomposition. Compose doesn't immediately recompose everything that's been invalidated. Instead, it schedules recompositions to occur efficiently. This typically happens at the end of the current frame, or when the system is idle. This batching helps to minimize UI updates and improve performance. Smart recomposition. Compose recomposition is smart because it only recomposes the parts of the UI that have actually changed. It uses information about the previous composition and the new state to determine which composables need to be re-executed. This helps to avoid unnecessary work. Stable versus unstable parameters. Compose checks if the parameters of a composable have changed before recomposing it. If a parameter is stable, meaning that its equals method returns true for the same logical value across recompositions, compose can skip recomposing that composable. Primitive types, example int, boolean, string, are inherently stable. Custom data classes should implement equals and hashcode correctly and be marked with @immutable or @stable if their properties never change after creation. This greatly enhances recomposition skipping. Asterisk phases of rendering asterisk after recomposition, compose UI elements go through following phases. Asterisk layout asterisk compose determines the position and size of each UI element. It does this by calling the measure and layout functions on each composable. Asterisk draw asterisk compose draws the UI elements onto the screen. It does this by creating a drawing tree and then rendering that tree to the screen. 3. Performance considerations and optimization strategies. While Compose is designed to be performant, it's crucial to be mindful of potential performance bottlenecks and apply optimization techniques where necessary. Asterisk minimize recompositions asterisk recompositions are the most expensive part of the Compose runtime. Reducing the number of recompositions is the key to improving performance. Asterisk state hoisting asterisk move state as close as possible to the composables that actually need it. This prevents unnecessary recompositions in parent composables. Asterisk use remember correctly asterisk remember is essential for preserving state across recompositions. However, don't overuse it. Only remember state that is actually needed to persist. For example, don't remember a simple calculation that can be re-executed cheaply on each recomposition. Asterisk use remember savable for configuration changes asterisk remember only preserves state within a single composition. If the activity or process is destroyed, example due to a configuration change, the state is lost. Remember savable uses the saved state registry to persist state across these events. Asterisk use derived state of asterisk if you need to derive a new state from an existing state, use derived state of. This ensures that the derived state is only updated when the underlying state actually changes. This code only recomposes the show button composable when the scroll position changes and the new scroll position is greater than 0. Asterisk immutable data classes asterisk as mentioned earlier, use immutable data classes and mark them with @immutable or @stable. Asterisk optimize layout asterisk complex layouts can be expensive to measure and draw. Asterisk flatten the hierarchy asterisk avoid deeply nested layouts. A flatter layout hierarchy generally performs better. Consider using constraint layout for complex arrangements. Asterisk use lazy column and lazy row for lists asterisk these composables are designed for efficiently displaying large lists of items. They only compose and lay out the items that are currently visible on the screen. This is crucial for preventing performance issues with long lists. Asterisk avoid overdraw asterisk overdraw occurs when UI elements are drawn on top of each other. This wastes processing power. Reduce overdraw by using opaque backgrounds where possible and avoiding unnecessary layering. You can enable Show GPU Overdraw in Developer Options to visualize overdraw. Asterisk custom layouts asterisk for very specific and performance-critical layouts, consider creating a custom layout. This gives you fine-grained control over the layout process. Asterisk optimize draw operations asterisk drawing can also be a performance bottleneck. Asterisk avoid complex drawing in draw modifier asterisk if you're using draw modifier to customize the appearance of UI elements, be careful not to perform complex or time-consuming operations in the draw function. This function is called frequently, so any inefficiency will be amplified. Consider caching drawing operations or using pre-computed values. Asterisk use graphics layer carefully asterisk graphics layer allows you to apply transformations, example rotation, scaling, alpha, to UI elements. However, it can also introduce performance overhead. Use it sparingly and only when necessary. Rasterization for static content that doesn't change frequently, consider rasterizing the content into a bitmap and drawing the bitmap instead. This can be more efficient than drawing the content directly on each frame. However, be mindful of memory usage. Profiling and debugging. Use Android Studio's profiler to identify performance bottlenecks in your Compose code. The profiler can show you CPU usage, memory allocation, and recomposition counts. Compose compiler metrics. Enable Compose compiler metrics to analyze the stability of your composables and identify potential issues that could lead to unnecessary recompositions. Add these lines to your build.gradle.kts file. Then, run assemble debug and analyze the generated reports. Recomposition counts in Layout Inspector. The Layout Inspector in Android Studio now shows recomposition counts for each composable. This allows you to quickly identify composables that are being recomposed excessively. 4. Code examples for performance optimization. Here are some practical code examples demonstrating performance optimization techniques. Example 1. Using lazy column for efficient list display. Lazy column only composes and lays out the visible items, making it very efficient for long lists. Example 2. Using derived state of to optimize state updates. Derived state of ensures that the show scroll to top button is only updated when the scroll position changes and the new scroll position is greater than 0. This prevents unnecessary recompositions. Example 3, using remember to cache expensive calculations. The remember block caches the result of the expensive calculation based on the input value. If the input doesn't change, the calculation is not re-executed, saving time. 5. Best practices for Compose performance. Write stable code. Write stable composable functions that produce the same output given the same input. Avoid side effects and mutable state within composable functions. Use the right tools. Use the Compose compiler metrics and the Layout Inspector to analyze your code and identify potential performance bottlenecks. Profile regularly. Regularly profile your app to identify performance issues before they become a problem. Stay up to date. Keep your Compose dependencies up to date. The Compose team is constantly working on performance improvements. Follow official documentation. Refer to the official Android Compose documentation for the latest recommendations and best practices. 6. Advanced topics. Sub-compose layout. This composable allows you to dynamically compose different parts of the UI based on runtime conditions. It's useful for creating complex layouts that adapt to different screen sizes or orientations. However, it can also be more expensive than static layouts, so use it judiciously. Side effects. Launched effect, remember coroutine scope, side effect, and disposable effect are used to manage side effects in Compose. Use these carefully to avoid introducing performance bottlenecks. Launched effect can be used to perform asynchronous tasks in a composable, but avoid blocking the UI thread. Integration with existing Android views. Compose can be integrated with existing Android views using the Android View composable. This allows you to gradually migrate your app to Compose. However, be aware that there can be performance overhead associated with bridging between Compose and the View system. Conclusion. Understanding Compose runtime behavior and applying performance optimization techniques are essential for building high-quality, responsive Android apps. By minimizing recompositions, optimizing layouts, and using the right tools, you can create Compose UIs that are both beautiful and performant. This comprehensive tutorial has provided you with the knowledge and tools you need to get started. Remember to continuously profile and analyze your Compose code to identify potential performance bottlenecks and ensure a smooth user experience. Good luck.